Hello and welcome back to Calculus 1, section 4.3. This is going to be, we're going to learn how to apply derivatives to function analysis. So we're going to learn about increasing, decreasing, min, max again, and we are going to also take a look at concavity. So we're going to do a lot of cool stuff with first and second derivative tests. Now, this in the textbook, the title is "What Derivative Tells Us," which is kind of funny title, so I kind of stay away from it. So 4.3. What do I have? Now, let's first see what are we talking about. So if I just take a look at some f of x that looks like this, I'm going to find the max point. And this maximum is local, right, relative. Then I'm going to find the minimum value. And if you look at this, the function is increasing here, decreasing here, and then increasing there. But also, over here, we'll say concave down, because it opens downward, and over here we'll say concave up, which is concave up opens up. Our job is to analyze functions using first derivative test and find the intervals on which the function is increasing, decreasing, concave up and concave down, which will also immediately tell us where the min and the max are. So that's the charge for this section. Let's talk about the rules. First derivative test. So for the first derivative test, we'll say that we have two rules for the first derivative test. So, let f of x be differentiable. On the domain. And now what you do is you say, number one, if f prime computed at A is less than 0, then f of x is decreasing. If f prime of A is larger than 0, then f of x is increasing. If f prime of A is equal to 0, we have critical point. Which is min or a max. We also have something else, but we'll deal with that later. This is what you have to memorize. Now, for this theorem, this A is what we call the test point. We pick this. So we pick it. Good evening. The other side of the bagel is ready. I mean the other half. This is all we need to know. Let's test this on the simplest possible function we can think of. That is a curve, which is
x squared.
X squared, exactly. And then we'll do spicier examples. So here's my f of x is equal to x squared. I want to know intervals of increase and decrease. Now, when I say interval, that means from x1 to x2 on x-axis. Let's do this. So clearly, I need the derivative. What's the derivative of x squared? Now we need to set that equal to 0 and obtain x equals 0. And we use, now I have to write that in blood as well. We use critical points and vertical asymptotes to partition the domain. Means nothing yet, but then we pick test values one in each partition. So note that x equals 0 created the critical number, right? It's 0. So that gives rise to critical point 0, 0. And I already said in this sentence that critical points partition the domain. So here's it visual. 0. So now I pick -1 and +1. I pick a value in each of the partitions. Partition is a part of the whole, right? So what you have now is you have that your domain is from -infinity to +infinity, and you also have that is cut so that you have -infinity to 0 on one side, and that's the entire section for the partition, and then you have another one on the other one, 0 on the other side, which is 0 to infinity. So now this is the first derivative test. First derivative test, f dt. You will take your f prime and compute that at -1. That's 2 times -1, which is -2. When derivative is less than 0, which means a negative number, the function is decreasing. So I know that the function is decreasing, and I draw that on the interval -infinity to 0. Why do I know it's exactly that interval? Where I use -1 as my test point. So this is what I said, you get to pick a test point, whatever you want, but it has to be one in each. Has to be one in each of these partitions. So now I will do the first derivative test at 1, and I will get 2 times 1 is 2. So this is smaller than 0 over there. This is larger than 0 over there. So larger than 0. Function is increasing. Function is increasing. So this is what I have. I was able to determine that there is a decrease up to 0 and increase after 0. Now, what does that tell me about 0 itself? Yeah, what is the critical point? It's a minimum. Do we all see the necessary behavior for a minimum here? Function is decreasing, becomes increasing. That spells minimum right there. We get that for free, right? In 4.1, you had to calculate surrounding points to check if the y value is bigger or smaller than the critical point and make the argument, right? It was annoying. Now, with this, you get it for free. Because if I have a decrease followed by increase, that's a minimum. If I have increase followed by a decrease, increase followed by a decrease, it's a max. But you can always visually check over there and you got it. So we know there's a min at 0, 0. You get the y value right by plugging the original equation. Very good effort. So that's what we have. We have a procedure here. We have a theorem, and we have a procedure. Procedure simply says, figure out your critical points, and you know your asymptotes. So critical points plus asymptotes partition the entire domain. And then pick a test point in each one of them, and then once you have the test points, use them in the first derivative because you are working on the first derivative test. That should make sense. All right, let's take a look at some problems from the textbook, and then we'll go and do the second derivative test. Where is the homework over here? There we go. Check if the function is increasing, decreasing, mean and max, and all that stuff. What do we have? Give me a problem 19 through 37. 19 through 37. Come on. 27. 27 it is. Beautiful. Look at that. F of x is equal to negative x to the 4 over 4 plus x cubed minus x squared. So this is the function. Again, what are the intervals of increase, decrease? Oh, I didn't write that for the previous problem, didn't I? This is terrible. I forgot to say that from negative infinity to 0, f of x is decreasing. From 0 to positive infinity, f of x is increasing. And that's your actually answer. You know, minimum or no minimum included. That's that. So now we're focusing on a new problem. The first order of business is to find the derivative, because you want to set it equal to 0 to find all the critical points. First off, as you're looking at that problem, it's a polynomial, so clearly it doesn't have any vertical asymptotes. You have to be very careful with vertical asymptotes. They partition as well. I'm going to do that in the next problem just to make sure everyone is good. So what's the derivative over here? Exactly. Very good. Your job is to set this equal to 0, maybe do a different color, set this equal to 0, and solve the resulting equation. So how do we solve this? This negative x cubed plus 3x squared minus 2x equal to 0. What do we do? Anyone? Very good. We'll do negative x, but yeah. Factor out negative x. We have x squared minus 3x plus 2. And now, does this factor? Factors as x minus 1 and x minus 2. Set each one of these factors to 0. We get x equals 0 back. X minus 1 equals 0. That's x equals 1. And x minus 2 equals 0. X is equal to 2. So I have 3 solutions now. Oh, by the way, did I ask you to warm up? I didn't, right? Yeah, good luck with the rest. So after all this work, we are finally ready to take a look at the first derivative test. Well, all of this is, old stuff. So f dt. We have a number line, and then we have important numbers. 0, 1, and 2. Remember, partition every one of these. So what do we do now? What do we do now? Pick test points. Great. I'm going to do that red. So clearly negative 1, that's the easy one, right? In this negative infinity to positive infinity. There's also number 3 over here. Who cares? What else? Which number should I pick between 0 and 1? 1/2. And how about between 1 and 2? 1.5, which is known as 3/2. So now my first derivative test, f prime at negative 1. Now this is going to be long and painful calculation. So we have x cubed plus 3 Where did I put this problem? Oh, there it is. You know what? Let me just write real quick the whole problem. Plus 3x squared minus 2x. Okay, there we go. So now I just copied the derivative because I have to do first derivative test. I don't want to flip up and down or pages, so on. So we have the function for the derivative and we have the test value, the red ones, that we need to test. So we do one at a time. So f of negative 1 is going to be 1 plus 3 minus plus 2 for a total of 6. It's larger than 0. And we have increase on that edge. Now remember, these are your partition walls. And this linear calculation gets to be stuck in this partition. So what's next? Next number is 1/2. So f of 1/2. And that is going to be what? Negative 1 over 8. Then we have to do plus 3, and now this one is squared, so I have 1/2 square. Oh, I should include a 3, right? No. And then minus 2 times 1/2. F of 1/2 is equal to negative 1 over 8 plus 3 over x to the 4. And then finally the mixed fraction over here, 2 and 1/2. Five halves. Common denominator is 8. So that's negative 1 plus 6 minus 20. And we have 13/8. That's bigger than 0. No, it's negative 13/8, right? It's negative 20. Exactly. Just leave it up to me to catch my mistakes.
Professor, should it just be 1 instead of 5 halves?
Yeah, is that supposed to?
Just 2 times.
Oh, it's a
not 2 and
multiplication.
1/2.
Yeah.
I was like, I haven't seen something like that since I was in high school.
Exactly. 2 and 1/2 and 2 times 1/2, they're very different things, because actually this one is equal to 2 plus 1/2, which is definitely not this. Sure. Yeah. So this is less than 0. So we know that on this particular interval, right, we have a decrease. Whee! Now 3/2, which is in between 1 and 2. So 3/2. F prime at 3/2. Anyone talk to me? No. So we have negative 3 cubed is 27 over 8. Yes. Plus 3 times x squared is 3 times, so that's 27 over 4. And negative 2x. Yeah, negative 2x, right? So that's going to be 6 over what? Come on. Over 2. Fix this common denominator, which is 8. So we have negative 27 plus 54 minus 16. So now, minus 27 minus 24 is 50. Very good. So that's negative 51 plus 54 divided by 8, which is 54 over 8. Cut this in half. 27 over 4. What is 27 over 4? I need to circle it. It's bigger than 0. That means increase. Yay. Will you always have this situation? Alternating, increase, decrease, increase, decrease?
No.
No. No is the right response because of the next question. All right, so we can, and we have one more, guys, and that's this region here. I didn't put the test point. I'm just going to use 3, because why use fractions if you don't have to? Who said that? Get out. Well, what are you going to do with pi cubed? I'm going to use my calculator. The whole purpose over here is to honor our ancestors and not use calculator. For half of the chapter 4. So, you have computers today, so... Well, I know. So, how about... wait, didn't I disqualify you from giving me the numbers?
Maybe at one point.
Oh, it expired? You are banned again.
How long is that time?
Well, at least 3 months. So we have negative 3 cubed. Plus 3x squared, so that's 3 times 3 squared. And then what do we have at the end? Minus 2x, so minus 2 times, this is a plus over there, right? 3. Do you see that these two drop right over the bat? We get negative 6 less than 0, so decreasing. So the function should look something like this forever. What have we discovered? We discovered that your critical point at 0 is a max. Just look at the, right? That's a max at 0. There you go. So that's a max, and that's a min, and that's a max.
Does setting the derivative equal to 0 find all of the critical points?
Yes.
The entire...
No, unless you have some from not differentiable. Sure. So the answer is no. Now, I'll write the answer in red. Answer. So this is what I'm looking for if you guys decide to have an exam. F of x is decreasing on, and you write the interval. So decreasing 0 to 1, 0 to 1, union 2 to infinity. F of x is increasing on negative infinity to 0, union 1 to 2. That's it. That's our problem. Our next problem is to take a look at the function f of x is equal to 4 over x minus 3. Maybe you can try this one on your own for about 18 seconds. The steps are the same. Derivative. Critical points. Remember partitions on vertical asymptotes as well. So critical points and vertical asymptotes, if you have them.
But it,
All right. Let's take a look at this problem together. I hope you are not doing the quotient rule on this derivative. We can rewrite this as 4 times x minus 3 to the negative 1 and then just do basic chain rule on it. So f prime of x is negative 4 x minus 3 to the negative 2 times the derivative of the inside using the chain rule is 1. So the whole thing is, no coughing, negative 4 over x minus 3 squared.
Do you get the same thing if you do a quotient?
Yes, you do. It's just much faster this way. But cool. And now, when you set this equal to 0 to find critical points, you immediately see that there's no solution here, because when you cross multiply, you get negative 4 equal to 0, and you know that's not true. So, no crit points. Now, does this mean that we don't get to do anything? No. We have vertical asymptote at x equals 3. And we partition there. So your entire domain is partitioned at 3. From negative infinity to positive infinity. Partitioned at 3. So what are my test points? Well, I would definitely use 0, because that's always cheap to compute. Can you use 1 or 2? Sure. You can also use pi over 2. All right? You can use e, or e squared divided by 4. In your case, I know that would make you very happy. For the rest, use 0. And then we can use, on this side, we can use 4. Yeah, I know. Actually, you know what? Please use Avogadro's number. Right? You're gonna.
At least that was a real number. Well, rational.
I know, right? So here we go. 6 point times 10 to the 23, right? All right. So now we have our first derivative computed at 0. First derivative is given as negative 4 divided by negative 3 squared. This is going to be, see, I don't care how much this is, right? Negative 4 over 9. All I care it's less than 0, so I can draw my decreasing there. That's all I care about. And then the derivative, first derivative calculated at 4. That's negative 4 over, and now I have negative, so 4, what do I get there? 1 squared. Well, that's negative 4, also less than 0, so I have another decrease. There we go. Now, does this make sense? Yeah, because we know what the function looks like. So.
Well, when you compute the derivative, how do you make that 4 negative?
Because the exponent drops as a negative 1 when you take in the derivative, right? And then minus 1 is minus 2.
Okay.
Yay. So all we have is that f of x equals 4 over x minus 3 is decreasing on negative infinity to 3 union 3 to positive infinity. It's decreasing everywhere. That's the answer. Now you writing this is what scores you 2 points for the final. Everything before that is partial credit. Now, is this confirmed? Of course it's confirmed if you draw the graph. We know what the 1 over x looks like. And now, since we have this minus 3 in the denominator, that means everything gets shifted to the right 3 units. So our vertical asymptote is here, and then we draw 4 over x. And there we go. Do we see it's decreasing all the time? We do see it's decreasing all the time. So that's good. Nice. That was a quick confirmation that calculus works. Do they have any ln problems over here? I know how much you love that. Ooh. Nice. 38 or 40? 40 it is. It says f of x is equal to x squared minus 2 ln x. So what are the increase, decrease? Oh, by the way, I'm sorry, previous problem. Do you see that there are no min and max? You see how everything kind of clicks in? It's so awesome. You look at that graph, you don't have situations that create min and max, right? That creates max, and this creates min, right? When you have them follow this way. Look at these two. They both go down. So they don't create situation. Also, it happens on the vertical asymptote. Could you have a point on the asymptote? No, you can't, right? Vertical asymptotes cannot be pierced. So you can't have a point on that asymptote that is a min or a max. So it's like everything clicks in, right? The derivative and the function and the graph and the critical points analysis, and everything is decreasing, so no min, no max, like everything is intertwined. All right, let's go with this one now. You know what to do. Same steps. Okay, let's take a look together. We take the derivative immediately. F prime of x is 2x minus 2 over x. And then we set that equal to 0. When you have a situation like this, then 2x is equal to 2 over x. When you move it to the other side, you cross multiply. So 2x squared is equal to 2, from where x squared equals to 1. And x is plus minus 1. Now, why is it important to know about the domain from pre-calc 1? Well, if you paid attention in pre-calculus 1, you know that domain for ln x is from 0 to infinity, which allows you to disregard -1 as your critical point. You can't have min or a max on that side at all, because function is not defined at -1. Now, let's say that you calculated things. You are going to get some either weird stuff or wrong stuff, right? Results, if you keep it. So, here in blood, due to the domain of ln x, which is 0 to positive infinity, we drop x equals -1 as a critical point or number, critical number. So now, what is my partition actually? Well, my partition is now starting, there's a wall there. It's starting at 0, it goes, and then I have partition at 1. So my critical values, my test points to check, 1/2 and let's say number 2. Those are the two values that I want to test. So I hope you guys see that this is the domain 0 to infinity. So my f prime computed at 1/2 is, what did I have over there? I had 2x, so 2 times 1/2 minus, or plus, what was it? Minus 2 over x, so 2 over 1/2. This is 1 minus 4, which is equal to -3, less than 0, decrease. F prime computed at 2 is 2 times 2 minus 2 over 2, which is 4 minus 1, which is +3, larger than 0 increase. What did we learn for number 1? Anyone? It's minimum, thank you. Thank you for being the part of this class. I feel very alone. And I say, well, so what's at 1? And I'm all excited, and just crickets on the other side. Svr, svr, svr. So thank you. So what do I have? I have a minimum at 1. So what is my answer over here? Answer is f of x is decreasing on 0 to 1. F of x is increasing on 1 to infinity. So you give intervals of increase and decrease. That's what's required in this section. The next part of this lecture is to talk about second derivative test, which is going to be identical procedure that will calculate different concept. So, get the second derivative, set it equal to 0, get the points, partition, test, points, test, and done. Same exact steps, different concept calculated. That's that concavity we talked about. So, second derivative test. SDT. So now we will talk about those concavities. So let's go with the theorem immediately. Let f of x have a second derivative on the domain number 1. If the second derivative computed at a is bigger than 0, then f of x is concave up. Number 2, if second derivative at a is less than 0, f of x is concave down. Number 3, if f second derivative of a is equal to 0, we have an inflection point. At x equals to a. So this inflection point is the new creature. It falls in the category min and max as a critical point eventually. We haven't discussed it so far, but I have to address it because you are going to run into problems where your first derivative is giving you a critical point and you know it cannot be critical point as a min or a max. Let me give you the cheapest example in a galaxy of that, and that is x cubed. Right? If you have just y equals x cubed, the graph for it is the squiggle. Right? Looks almost as a tangent function. Right? It's not periodic, no asymptotes, it just looks like crazy. Right? So, what is the first derivative for this? What's f prime of x? 3x squared. And when you set that equal to 0, what do you get for x? 0. You see? First derivative equals to x gives you x equals 0. Now look at your x equals 0. It's right here. Does that look like a min or a max? No. Right? Yeah, and you are going to get increase followed by increase. So it can't be, right? There is no change. You only get increase, decrease, decrease, increase, right? But this is going to be increase, increase, because if you look at the function. So see, there is the trick. So what is this x equals 0? Well, it turns out that it's inflection point. What is an inflection point? Inflection point is a point at which concavity changes. So, this point over here is not min or a max. We see that from the picture as well. But if you take the second derivative, which is going to be 6x, and set that equal to 0, you will get x equals 0. And now that's inflection point. And now here in red, inflection point is a point at which concavity changes. I had that before. I never said what it was, but that first graph we had, this one, right here somewhere is an inflection point at which point concave down becomes concave up. Do we all see that? Because on this side, you have, on this side here, you have like a cup that holds the water. It's concave up. You can fill it with water and the water will stay. The one on the other side is concave down. It spills the water. Right? It can't hold the water. It goes downwards. So those are the two possibilities you have. And now we added to this mix, we added the fact that if it's equal to 0, you have the point at which the concavity changes, and that's called an inflection point. We partition over all inflection points and all vertical asymptotes. Remember that the vertical asymptote is preserved when you take the derivative from a function to the first, to the second, to the 37th derivative. The function will always, the vertical asymptote will always be in the same spot. So now we go all the way back to our problem, and we also say here, partition over all inflection point and all vertical asymptotes. Ta-da! So now, to finish off my x cube example, since I'm already there, my negative infinity to positive infinity domain is partitioned at 0. I will pick two test points, -1 and +1, and do the second derivative test. F double prime computed at -1 is 6 times -1, which is -6, which is less than 0, which is concave down. Second derivative computed at 1 is 6 times 1, which is +6, which is bigger than 0, which is concave up. Does this make sense when you look at your graph? And the answer is yes. Do you see how for the part before 0, right, from -infinity to 0, you have a concave down? You can complete the other side into a parabola that opens downwards, right? You can do that. And it becomes concave down. So now what's the answer? We say f of x is concave down on -infinity to 0. F of x is concave up on 0 to infinity. Now you would go really, do I really need to have a second derivative in addition to all? I already see increase and decrease. Isn't that enough? Like, why would we have second derivative test? What is it good for? What is the concavity good for at all? Why bother? Well, do we have some business people over here, business-minded people over here? I want to ask you, business people, to analyze 3 graphs for portfolios, 3 portfolios that are money related. So what do I have? I have graph number 1, which is money in time. I have graph number 2, which is money in time. And I have graph number 3, which is money in time. The first graph, they're all going to start at the same investment of, I don't know, 10K money. So everyone is going to invest 10K money. One portfolio is going to be like this, one portfolio is going to be like this, and one portfolio is going to be like this. Where do you invest? Which portfolio is the best portfolio in case of this? So far I have bottom and middle. No one is voting for number 1?
Oh, wait.
I'm waiting.
Do I get to, imagine as if time will go past that graph?
Of course, time will pass.
Oh, well, yeah.
Maybe if I add the arrow over here, meaning it allow we wait infinite time. Yeah. So which one are we settling on? We are settling on concave up graph in the middle. So now look at this, guys. Second derivative is positive, second derivative is negative, second derivative is 0 because it's a straight line, right? See that? What's the first derivative of this? Is the slope of the line. Let's say it's 3. The slope of the line is 3. You're making $3 per minute on a constant, right? But there's no concavity there because the derivative of that slope is 0 when you hit the second derivative. So no concavity. Concavity is 0. And look at this one. Right? This one is making, this is exponential graph. Exponential graph. This is a logarithmic or a square root graph. They're sluggish. Yeah, it's start. Right? This is basically how, this is how you do the coursework in high school. Right? Like, I got this. Right? And then by the month 2, you're like, yeah, back to 38. But I had 100 on the first 2 exams, I know. Which is why in my class it's 10 and then 13 and then 16 to kind of, eradicate that behavior. So, first off, which graph makes money? All of them. All of them are making money because the second point, you take a look, is taller than the first point of investment. All 3 of these are increasing. All 3 of these have first derivative bigger than 0. You still want to invest in the second one and not in the other ones. And the only differentiation between these 3 graphs then in that case falls to concavity. Go ahead, find your engineering, right, applications when you are charging batteries and other things to see which way do you charge the battery. Is it going to be this way or that way? It's definitely never this, right? What do you think? Charge the battery, is this one or that one?
First one.
The first one, exactly. The second one is, that's what the second one is. The second one is going to try to to feed in more and more and more energy. What happens as you start filling stuff up? It's harder to fill those little leftover percent, right? Your chargers are fast chargers. They're gonna go and plow to 80, 90% of the battery, and then they're gonna go, okay, +1, +1, +1, right? So you see that. Would both of them charge? Sure, right? So the first derivative is increasing. What are we increasing? Energy stored, right? You are converting electrical energy from the outlet into chemical energy of the battery until you change all of the chemical structure of the battery, and then when you disconnect and plug into the device, chemicals in the battery are converting back from chemical into electrical. It's a very simple process. Great. So now we understand a lot of that stuff. And we understand that we have a need for second derivative test to get us to pick charging or portfolio investments or so on. Go ahead and find the application in your own field. Let's take a look at the homework examples. Let's start with something that it's kind of on a vanilla side and then upgrade. So 83. Remember, you have to go through second derivative, so first and then immediately second. Let's go with problem 83. F of x is equal to 2x cubed minus 3x squared plus 12. Concave up, concave down. No one said anything. I mean, we still have time. But Thursday first? Or no? Did we set up the date for the test or not?
Next Tuesday.
Tuesday. I thought it was Thursday.
Maybe it could be Thursday at this point.
No, the week of Thursday.
We didn't do the review, so.
So are we gonna do the Thursday?
Why are you asking me? Because I need to know if the quizzes are starting tomorrow or they're starting on Friday. That's what I need to know. Depends on when the test is, yes.
When's your dinner?
I'm sorry?
When's the dinner like day?
Thursday. Tomorrow, 2 days.
This Thursday.
2 days, yeah.
Okay, then why don't we just have our test Thursday?
Yeah, that works. Yeah, it should be next Thursday if we want to do a review day.
We'll do a review day on Tuesday.
It's not going to be a review day. It's going to be in class. You can answer any questions, problems. Yeah. Lab time.
That works.
So is everyone okay for Thursday then?
Yes.
We're good with Thursday?
Hopefully I'll feel better about that.
Oh, it's going to be great. You can take all of them.
Unless I don't run that class by next week.
I understand.
So yeah, well.
Okay, good. So then your quizzes will start on Friday. Quiz 1. Quiz 1 on Friday. What's the date? 26th?
Yeah.
Quiz 2, Saturday, and so on. Good. All right.
I can see those. Zero is closer than I just use the closer.
Great.
Yeah, you get the same answer.
Do we all have x equals 1/2?
Yep.
Great. So this is a polynomial, so no vertical asymptotes, no anything weird happening anywhere. We have from negative infinity to positive infinity in terms of our domain. Sorry, we partition at 1/2. So the test points are 0 and 1. So if the test points are 0 and 1, we have second derivative calculated at 0. That's 12 times 0 minus 6, which is negative 6, which is less than 0, concave down. And the second derivative at 1 is going to be 12 times 1 minus 6, which is 12 minus 6, which is 6, larger than 0, concave up. Now we're going to take all of this, and in the next section we're going to learn how to graph any function by hand. Because I can involve trig, I can involve e to the x. Let's do one with e to the x because you love it so much. And we can actually graph. So just move to the next one, 84. F of x is equal to e to the x over x plus 1. Perfect. Gonna love the second derivative on this, the quotient rule. Do we all have the same first derivative?
Yeah.
Yeah. Good.
Yes.
What do we do for the second derivative? Do it again?
I was thinking it's not that.
Another quotient rule? Please kill me now.
Chain rule.
Again.
Yeah, there's things in there.
Anything easier?
Logarithmic differentiation, exactly.
Oh, right.
Right, designed to just ruin this. Right? So second derivative using logarithmic differentiation is x e to the x divided by x plus 1 squared times the derivative of this, which is 1 over x plus 1 minus 2 over x plus 1. There you go, done. Yeah, I know. I didn't ln both sides. I skipped 7 steps, but it's okay. This is the power of logarithmic differentiation. Now, by the time you get your ducks in order, which are product rule, chain rule, and quotient rule, you know, the life already passed. So, for logarithmic differentiation, you copy the function as is, and then you have ln x, its derivative is 1 over x. You have ln e to the x, which is actually x ln e, which is just x, so the derivative of that is 1. And then finally you have 2 ln x plus 1, and that's that. So it's very fast to take this derivative, and all you need to do now is to set this equal to 0. You have x equals 0, you have e to the x equals 0, and you have 1 over x plus 1 minus 2 over x plus 1 equal to 0. So these are equations you have to solve. First one is already done. Second one has no solution because your e to the x never crosses x-axis, so it's never 0. So there you go. The only one you have to work on is the last one. There are a number of ways in which you can work on this. I would suggest to add these two, move this one over, and then use the cross multiplication. So when you add the first two, you will have x plus 1 over x. Move this one to the other side to get 2 over x plus 1. Cross multiply into x plus 1 squared equals 2x. Expand this into x squared plus 2x plus 1 equals to 2x. X squared plus 1 equals to 0, no solution. Yay. Because it's quadratic, you can't factor it, right? Square root of -1 is complex. X equals 0. Yay. That's our inflection point to go ahead and partition around x equals 0. While we're still done. It's called mathematical gymnastics. I don't know if you practiced it. The art of mathematical gymnastics, but there you go. Remember algebra when this was like each one of these was a homework problem? And now it's just stuff to the margin. Oh, you missed those days now, right?
I mean, it doesn't matter. It's going to be.
I like the idea of us having slopes.
Oh, this is. I'm fine with I mean, I'm going to be here. I get out a lot, but
It's like about how civilizations
look at how much so let's say this is type 0 that was I just get on
so a facilitation has a technology. One thing already got this if they wanted to. Couldn't they?
I was so mad because I spent like half an hour with no problem, and then I just didn't put the program in the box, like in the right place. It told me how it was wrong.
It was probably 7 seconds of single analysis that said there is actually no intelligent way move past like
Super plans.
not even because they actually can actually observe that this is we're going to go left or right. There's no colonies. Trying to find it. I don't think any day. Create a web group so we can.
Actually showed this class. Eric was here.
It's an extra.
What they should do, they should be doing stuff like this. Show me the categories.
Yeah,
How's that like?
That's what
That's what I think. Is showing the decisive. I'm gonna do this. And it's like that for like
It's it doesn't look like electrical. You suck.
It's supposed to, that's what it's like supposed to be for that.
I don't want to do
One little rock and like this one. With like pads and pads.
I think we should try to get to that.
And I love what
that
CEO said.
But that was no way. The last one is that was at the end of the time.
They have been.
Born one of those companies that have been let's go now.
It was wrong.
The trick is they don't even have to wait. It's just
Probably down in the business. Most people though.
It's like
Or also like people that are
and that is why. That's why.
Nothing on you.
It's like you have rocks and then even more rocks.
So we have x equals 0. We do the partition on x equals 0. And what else do we have? We have a vertical asymptote at -1, right? So as we do our partitioning now, second derivative test partitioning, we go from -infinity to +infinity, and we have a partition at 0 and partition at 1. No, -1, thank you. So -1 and 0. So these are the two partition values. One is the inflection point and the other one is vertical asymptote. So once we have the partition values, then we have test values, -2, -1/2, and 1. Those are the test values. And now we check this in the second derivative. Now note that the second derivative is, for the lack of the better word, very interesting, right? Do we care about the value? No, we don't care about the value. We just want to know whether the thing is positive or negative as we compute these. So let me go and copy the second derivative over here, which is x e to the x over x plus 1 squared times 1 over x plus 1 minus, if I remember, 2x plus 1. That good? Yeah, fine. So now, what do we know? Please observe that e to the x is always positive, because e to the x graph is always above x-axis, so that's always positive. Denominator is also always positive because it's squared. We don't have to waste our energy computing those. So what I can focus on is just x times 1 over x plus 1 minus 2 over x plus 1. That's the only thing I need to focus on computing as I do my second derivative test, because this is going to give me some kind of a sign. So to test the second derivative at -2, all I need to check is the sign of -2. That's a -1/2 plus 1 minus 2 over -2 plus 1. So this is going to be -2 times, and I have now 1/2 minus, and this is 2. Negative times negative is positive, so I'm done. Concave up. You see, I don't care about computing any of these things. I just see 1/2 minus 2, that's negative. I don't care what the value is. Negative times negative is positive. I'm done. Then the next value we want to test is -1/2. So that's -1/2 times, and I have 1 over -1/2 plus 1 minus 2 over -1/2 plus 1. Compute this. So I have -1/2 times, this is -2 plus 1 minus, now multiply top and bottom by 2 for this double fraction to kill the double fraction. So when you do that, you get 4 over 4. 4. You just get 4. That's all you get. 4. Because you have 4 over 2 minus 1. Yep, that's 4.
Professor?
Yes?
Sorry, in back when you used -2, you said it you had 1 over 2 minus 2. Should it be 1 over 2 plus 2?
This gives you positive half, right?
Yeah, that's positive. The other side is negative, negative. So it's plus. So you
The
have
other
plus
side is
0.
plus.
Yeah, you have minus and negative.
Oh, yeah, it is.
So it's greater than that.
So it's less than 0.
Yeah.
Okay, thank you. Well, that changes this u into d. There we go. Thank you. That's good. So now what we have over here? I have negative times negative. That's a positive. So now concave up. I hope that was valid. And then the last is plus 1. So second derivative at 1, that's going to be 1 times 1 plus 1 minus 2. I'm getting a 0, and that's not good because then it's a critical, and then it's an inflection point, right? Oh no! Oh yes. Hold on.
Here's -1.
Oh, over here, -1?
No.
When x is equal to 1, we have 1, 1,
Oh yeah, it's 1.
2 over 2 is -1. Thank you. So the value is 1. Larger than 0, so another concave up piece. Whew. Good. Bye.